Hi, my name is Jan Ketil Rød, and I am a professor in Geographical Information System and Science at the Department of Geography at the Norwegian University of Science and Technology. I have 3 videos about map projection and coordinate systems, and this is the second one, which will deal with map projections. Most of the content in this video lecture is taken from the textbook GIS Tools to Understand the World. Map projection is about how to transform coordinates from a spherical surface to a plan map. And in this video I will talk about types of map projections. These can be divided into plan, conic or cylindrical. I will talk about errors in projected maps and some of the qualities one wants to preserve. So you can make conformal maps which are used for navigation because that equals bearings from a spherical surface to the map. You can create maps that are equal area, so that an area on the spherical surface equals the one in the map. Or you can make equal distance map, where one distance measured on the global surface equals the distance measured on the map. Common for all of these is that maps will be distorted, and very much so for conformal maps we will have distorted areas. So I will give some examples of that. And true equidistant map projection do not exist. So there are some restrictions involved, and I will talk about these and as well present an alternative, the geodetic ellipsoidal distance measures. And then finally talk about compromise projections, where actually none of the qualities are preserved, but they are all tried to be minimized. There are 3 types of map projections, and we call them plan, conic and cylindrical. Since the Earth is double curved, it cannot be unfolded. And in map projections, therefore, points on the spherical surface is transformed to a point on a surface that can be unfolded. And a plan, conic and a cylinder, they are all surfaces that can be unfolded. All 3 types of map projections introduce error, but the error is smallest at or near where the spheroid touches the plan, the cone or the cylinder. For the plan projection, the accuracy is best at or near the point, such as the North Pole. So these plan map projections are therefore often used to map polar areas. For the conic projection, the surface of the Earth touches the conic along a line, as illustrated here by the 30-degree latitude north. So the accuracy for a conic map projection is best at this tangent line or near it. Similarly, as for the cylindrical map projection, typically then equator could be used as a tangent line where the surface of the Earth touches the cylindrical form. And then the accuracy is best at or near equator. So at the equator, for the cylindrical map projection, we may have small errors, but the errors increases as the distance from equator increases, both towards the north and towards the south. So at the polar regions, we will have large errors in cylindrical map projection. The map should have certain qualities. The map should provide answers to questions like, what is the bearing we need to follow to sail our ship safe home? What is the area of protected land or any other area? And what is the distance between point A and point B? So it's the map's ability to answer such questions that makes a map useful. And map projection is typically designed to provide one of the following properties: conformal, that means that a bearing, an angle towards the north direction, is the same if you measure that on a spherical surface or on a plan map. And this is very useful for navigation. And equal area properties means that an area measured on the sphere equals the same area measured on the map. And equidistance property means that if you measure a distance between point A and B on a spherical surface, the same distance you will measure between the 2 points on a map. For equidistance map projection, these are true only for certain distances, which we will see later. And you can also have maps where none of these qualities are preserved, but where one tries to minimize the negative effect of all of them. And these maps are called compromise projections. So a map has always errors, and there are 3 important things to remember. A map can never be both conformal and equal area. If you have one of the properties, you will not have the other. So an equal area map does not portray azimuth angles correctly. A true equidistance map does not exist. But the reassuring fact is that at small areas, and then with small areas I mean within a UTM zone, these errors are neglectable. And you can measure areas, distances, and you can use the map for navigation, and it will be good. More about the conformal projection. This is the most common projection, and maybe because it makes navigation possible. So here you will have the azimuth angles correctly, but a conformal map does not portray areas correctly. And I will try to tell you why not. Using an example for a Mercator's map projection, which may be the most famous conformal projection. This is useful for navigation, but area are distorted. One of the reasons why is that the lines of latitude, the parallels, the lines parallel to equator, they have the same length as equator. And this is not true. So the norther you come, for instance 30 degrees north, 60 degrees north, these lines of latitude should be shorter than equator. The more north, the shorter the lines of latitude. Also towards the south, further south you come, the lines of latitude become shorter. But in Mercator map projections, they're all at the same length. Another issue is that on Mercator's map projections, distance between the meridians is constant. So this is also not true. At equator, they are the longest distance between the meridians, but as this goes towards the north or the south, they are meeting each other. So at the North Pole, for instance, all the meridians meet in a point, but not in Mercator's map projection. Then also up here north, the distance between them are constant. So these 2 issues put together result that the scale increases quite enormously towards the north and towards the south. And land areas such as North America and Greenland and even Scandinavia become extended. And the effect of this increasement increases with the distance from equator. So also Antarctica continent is huge on Mercator's map projection. I will provide some examples. From a Mercator map projection, Scandinavia becomes bigger than India. If we measure this from the area measures based on maps on Mercator projection, the total area of Norway and Sweden is larger than the total area of India. In reality, however, India is about as big as Western Europe. Another example, North America appears bigger than Africa in Mercator projection, but in reality, the relationship is about 2/3. And Greenland seems to be bigger than South America, whereas in reality, Greenland is about the size of Mexico. But it doesn't appear that way in the Mercator projection. Although the Mercator's map projection distorts the area as it does, it is a very popular way of portraying the world, and you can get these wall maps from IKEA. And many think that this contributes to our perception of the world, contributing to a cartographic suppression of African countries, South American countries, South Asian countries, being much smaller than the European, North American countries, which is a wrong perception. In 1973, Aldo Peters published his area-corrected map projection. Area-correct projections have been made since the 18th century, and although Peter presented the projection as new, it was very similar to Gall's map projection. The projection is therefore referred to as the Gall-Peters map projection. The new thing that Peter claimed about his projection was that the area distortion present in the dominant conform projection is corrected for in a manner beneficial for the so-called third world countries. And I think the occasion for publishing the projection in 1973 was very appropriate. It was a time when emancipatory ideas were widely supported. The United Nations and several non-governmental organizations embraced, therefore, Peter Mapp's projection because it was interpreted as emancipatory on behalf of the third world countries. Among conservative cartographers, however, there were several critical comments. And mainly these were because it was claimed to be the first area-correct map projection, and Peters claimed it was his, although it was very similar to the Gall projection. Someone also made a joke about the map projection by looking at the forms like Baja California, Florida, South America, Africa, India. These landmasses are somewhat reminiscent of wet, ragged, long winter underwear hung out to dry on the Arctic Circle. So I don't use the Peters map projection often. My favorite among the equal area projection is Eckert map projection. These comes in various formats, and I tend to pick Eckert 6. Now, equidistance property. This preserves then the property of distances, also called true scale. But true scale is not possible for any kind of lines measured everywhere. True scale is only possible for all lines passing through or radiating from a single specific point. Or you can have true scale along all meridians. Here we have a true scale maps where measured radiating from Schiphol are correct. I designed this map myself, and many GIS has the ability to make azimuthal equidistant planar projection where you pick the point of interest, and that will be the point where radiating lines will be equidistant. So here, any straight line radiating out from Schiphol airport outside of Amsterdam in the Netherlands has true scale. Now the other options for equidistance map projection is to have equidistance conic projection or equidistance cylindrical projection shown here, and both are then correctly measuring the distances from pole to pole along the meridians. So along these lines from the North Pole towards the south, either on the conic projection or in the cylindrical projection. Here we have true scales, and thus we have true distances. But any other distances that you may want to measure will not be accurate. So if you want to measure a lot of distances where the birds are flying or whatever, you can use an alternative. Use the geodetic measurement using the spherical geometry and measure these geodetic, or sometimes called ellipsoidal, distances on a spherical surface. This is now available also in most GIS. And this is from a study on armed conflict, where we are then measuring from the capital in each country to population centers of ethnic groups that are not in power and that may oppose to the government. Distances can also be measured in most GIS using the ruler tool, and then the geodetic distance in ArcGIS Pro will be displayed as a curved line. The ellipsoidal distances in QGIS is however not displayed as a curved line. Then the final type of map projection I briefly want to talk about is what we call compromise projection. Here we don't have any of these qualities of the map preserved, but all of them are tried to be optimized and the errors minimized. So Robinson was very popular for a long time among these compromise projection, but nowadays the Winkel Tripel map projection may be the one many uses. Perhaps especially after 2007, where this article here evaluated a lot of map projection and found indeed that the Winkel Tripel projection has a low distortion in most measures and overview quality assessed as excellent, and therefore being adopted by, for instance, the National Geographic when they are producing world maps. This is how it may look if made on a world map in QGIS. So this is available from the Coordinate Reference Systems menu. Now this was the end of the video lecture on map projection. You may already have seen the video about geographical coordinate system, which where then the location on the spherical surface and the map projection then is used to portray these on a Cartesian coordinate system. And the next video you should watch is then a video about the Cartesian coordinate system.